Hello, everyone. Thank you for joining us here today. My name is Michael Haag, and I am part of the Splunk Threat Research team. Today, we will be talking about hunting naked and afraid, shaking the stick at Cobalt Strike. All right, again, my name is Michael Haag. I'm a senior threat researcher here at the Splunk Threat Research team. I'm also with Jose Hernandez. Jose is our senior manager on the team.
So what does specifically our team, the Splunk Threat Research team, do? And why do we even bother looking at Cobalt Strike? Well, we studied the threats. In this case, again, Cobalt Strike being one of the threats. We'll talk about that in 1 second. And we take these threats, essentially trying to understand how they work. We break them apart, reverse engineer them in some cases, and try to simulate their behavior. Essentially with the intent of creating a data set from their behavior or their actions. With these data sets, we then are able to build detections for Splunk, as well as replicate and test these detections that we build consistently since we have these data sets. When we end up building these detections and codifying them, we're also then able to ship them across Splunk and their different products. And it's kind of what the primary thing our team does today, right? We ship detections for Splunk. In the process, again, of creating these data sets, building these detections, we've written tools for ourselves to make this process a lot easier. So we have open sourced them, and you've heard of tools, I hope, like the attack range, and we're maintainers of this public repository. That's another kind of key thing that our team does. And finally, we share all this with the community. We try to be as transparent as we can with our work and essentially try to help the community with their work. And so all of our detections are open source and free. So is all of the tooling that we end up using for creating them, as well as the data sets.
So for our agenda today, we're going to focus on what is Cobalt Strike, why do we hunt for it, ways to catch a Cobalt Strike team server, the architecture of our Melting-Cobalt scanning tool. We'll jump into a demo, and then we'll also dive into our detection development process. Cobalt Strike is a adversary simulation tool typically used by organizations with red teams that are attempting to simulate actual adversary tradecraft and behaviors. The thing that occurred, though, was that Cobalt Strike was leaked and actual adversaries began to use the utility. And on the right-hand side, this is from MITRE, you'll see that multiple different nation states and APT type groups are utilizing this product now. So why hunt for Cobalt Strike? Well, Cobalt Strike has been in the news for at least the last 2+ years now. Adversaries have been abusing it and everything like that. So the benefits for a SOC? Well, understanding adversary TTPs. We are able to see exactly how they operate. And with our tool, Melting-Cobalt, we're able to grab those malleable profiles and begin to generate new content. And we're able to see how they're changing their tradecraft based on those malleable profiles in the wild. It also helps us build better analytics. We're able to say, hey, like last month they were all using, or there was a higher degree of adversaries using a spawn 2 of run DLL32, but now we're starting to see a switch to DLL host or search protocol host or any other native Windows process. So there's a lot of benefits for a SOC in understanding and seeing and splunking malleable profile data or in the wild team servers. All right, so next we're going to talk about hunting the Cobalt Strike. So a couple of approaches we took here was we had two options. Scan the entire internet, which has decent pros, which would be finding real-time or active Cobalt team servers out there. It also makes us less dependent on services like Shodan or Security Trails or Zoomeye. And you could potentially go off and collect whatever you like because you're scanning the whole internet. Obviously, there's some cons here too. You're now in the business of scanning the entire internet. You need to find a friendly, air quote, friendly bulletproof provider. You need to wire up ZMAP or MassScan, and it's going to be kind of slow. It's not perfect. So the other option that we decided to take was, or looking at, was using third parties that already do this because they do this for a living. So take all the pros is everything from the last slide, the cons of, the last slide. Now we're taking confirmed active data from the last month or from the last time those services actually scanned. We can enrich that data out of the box. So there's pretty good reasons to go with a third party. Even today, Shodan now captures the malleable profiles or all the data from a Cobalt team server. So that helps us because it's already enriched. The con is, it's going to cost a little bit of money because now we have to buy a service and use that service. We're reliant on the last scan time that the service had actually scanned it. Most likely to find inactive team servers, but maybe good or bad. And sometimes inaccurate results, just depending on the time. So if you were to rescan it, it may not be there anymore. So a few of the methods that we use with Melting-Cobalt or a way to go and hunt for team servers is there is a lot of SSL JARMs out there in the wild. So you can hunt for them based on the JARM. There's a default JARM for Cobalt Strike. The Java application itself has a specific TLS or SSL JARM in the wild, so it's easy to go and scan for that. In addition, we can combine the JARM with, say, open ports. So if it's like 443 or different default ports that we've seen in the wild, things like that. You can also do with like Shodan and other services, the HTTP responses. So in particular, the default is 404 not found, and the content length is always 0. And then to be more granular or precise in our scanning, we could lock it down by region or even hosting providers or ASNs and things like that. You can combine all of these in your query and begin to find multiple things. You can find different JARMs, different open ports, different HTTP responses, and so forth, and combine all that to your next query that you perform looking for team servers.
So my parrot Rio here decided to join us. So how do you query a Cobalt Strike team server? And specifically, let's break down how this NSC script written by Wade Wiki works and how essentially it's able to grab a Cobalt Strike beacon config from a running team server. So an NSC script essentially is run by Nmap, and you will pass this like any other script right into an Nmap command line. And the major things that, again, you're going to operate from are either a host, which is an IP, or a port. And essentially, given this IP and port, grab beacon NSC script starts from there. The first thing it does is it tries to fuzz the URL the Cobalt Strike team server is potentially hosted on. And in this case, essentially after it's able to successfully match the fuzzed URL, then it tries to grab tries to make essentially a request to it, and if it's a valid URL, and return the response from that request. It then hashes those responses and essentially pulls out hex sections of the code, which are the different corresponding to different configurations of the Cobalt Strike team server, and it puts these configurations essentially into a Lua map or a JSON structure in essence, and it returns that JSON back to the user, right? Now, ultimately, that JSON kind of looks like this, right? You have interesting things like which callback methods that beacon was configured in. So is it using DNS? Is it using HTTP? Is it GET, posting, right? You also have things like what jitter is it talking about back on, what protocols, what is the DNS, if it's using DNS that's configured to point to, what is the command and control server is configured on there, and very interesting too, what is it going to spawn into in your EDR once that beacon infects your EDR, right? What process is supposed to inject into essentially. All this data is what we end up using to write a lot of our detections, and Mike is going to spend a lot of time on this, but invaluable to say the least, right? Now, we built this tool called Melting-Cobalt. Melting-Cobalt, again, we've open sourced it. Like I said, that's stuff our team does. It's free and on the Splunk GitHub. But essentially what it does is it does two things. It scans or uses third-party scanners like Shodan, like Security Trails, like Zoomeye, internet scanners to return a list of potential Cobalt Strike servers, and then it runs grab beacon or essentially this NSC script to pull those servers down. In short, you either pass a list of IPs or just pre-configure with the API tokens for its providers. It runs this function called mine-Cobalt, and we have already a list of pre-built searches against each of these providers that find what may look like a Cobalt Strike team server on the internet, right? So something, again, Mike is going to go into details of what that is, right? But after we get that result of essentially potential IPs or ports that are Cobalt Strike team servers, we then run, again, grab beacon under the hood by calling mmap programmatically, and then extract those results, put it into a dictionary, and write it out to a JSON file in the system. Now, the cool thing with this JSON file is that we can use for a lot of analytics and really study Cobalt over time using the scanner. And we'll dig into that data in 2 minutes. All right, to get started here, first we're going to visit Splunk, Splunk's GitHub, and go to the Melting-Cobalt repo, and we'll clone down the repo. So check it out. Now, if we quickly open the Melting-Cobalt configuration file template, and to do this, again, to get started, you simply copy over the conf file, remove the template extension, and really the only required configurations here are the actual API tokens. You can also see the search at YAML. So we'll get started with security trails and Shodan as our internet search engines. On the search at YAML here, you see the different search parameters. We search for things like the JARM hashes, ports, search serials, and it allows us to pull back potential Cobalt Strike servers. Again, if you recall the diagram, that's the first step of the tool, just figuring out what are some potential public servers out there. Next here, we're gonna just quickly install a virtual environment to get our dependencies for the tools going. Again, super straightforward, just virtual env if you have it installed, and Python pip install the requirements. And here we should have an executable tool in a second. Perfect, yeah, so here you can see we can bring up the help. And by default, it reads the conf file that we copied over, and if you just run it, you immediately see it already returning results. So for example, the first query in Shodan returned 181 results, the second one, 1,228 results. So the tool is parsing through all of these results, grabbing all the potential Cobalt Strike hosts found out in the internet, and then it immediately starts trying to figure out or extracting out the beacon information from them. So you can see here, there's a bunch of them that fail. That means that when you try pulling down the beacon, there wasn't a beacon there, it wasn't responding, or whatever the case, they'll print out the error. But if it is successfully able to pull up the beacon, it's going to save it locally into a results.conf file. Results.log file. We'll read it out in a second. So here it found 140 beacons as a result, which is pretty awesome. And again, if we cap this results.log file, you can see it's in JSON format, so neatly formatted, and we have stuff like the C2 information that the beacon had, what callback methods it was, what IP. We even store down the specific mmap command we run to get this beacon information under the hood, but the tool runs under the hood. Now, and again, to confirm, there was 140 results written down. Right? So hopping quickly over here to Splunk, if we index this data, and I already brought it in, and again, if you tell Splunk to just index it as JSON, easily parsable out of the box, right? So KV, I think it's KV mode JSON on the props.conf file. It will neatly parse out the data, and we have this now all in Splunk. And again, the cool part here is now we can do cool analytics like, for example, the most indexed host name, host header from these beacons was jQuery. Stuff like the spawn2. So what spawn2 is the different beacons, or what processes are different beacons spawning into. You can look at the, like stuff like rare over time and do essentially statistics with this kind of data. Now, what we've done is, with all of this, we've gone ahead and actually build a dashboard. So here, I'm going to just quickly jump over to it. And in this dashboard, maybe you can see that the first graph is we're tracking watermarks over time. And the cool thing is we've seen over time, we've been collecting this data for about 6 months, and we've seen different watermarks drop off, which is great. Also, watermarks is consistent to the commonly cracked versions. Of course, more crack. The second table here, as you see, is the C2 host headers, which gives you a high visibility into what the potential malleable profile that the actor used. Again, you see jQuery being I think it's a Threat Express profile most commonly used. Also, you have the top ports that we discovered these beacons on. Again, I would expect them mainly to be 443 to 443, and also the DNS idle. This is good because since this is the beaconing, basically this is when the DNS beacon sits idle. This is where we'll beacon to. And finally, the spawn2 and the rare spawn2. These are the top processes that a beacon will spawn for its post-exploitation activities. And the rare spawn2 is on the right here. It gives you, based on the different collections, on the collections of profile we've collected, you have a small chance to come up against these spawns2 process. There's a greatest chance you always see a run DL32 by default, which is a default spawn2, or a DL host, which is found in many public malleable profiles.
Awesome. Thank you, Jose, for that great demo. Okay, now we're switching gears. We're going to begin digging into detection development, how to write content based on what we found from the malleable profiles. So something that we can do, because Cobalt is leaked and based on everything we've found, we can simulate Cobalt Strike activity. We can also use the different profiles that are out there on GitHub. We can review this data for patterns or behaviors, generate content based on that. So this will be our new detections. And so as defenders, we have to watch every angle. And in this particular case with Cobalt Strike, I kind of classify it as three things we can get out of these malleable profiles. We have pipes, named pipes, DNS, or any kind of network type data, URL, URI, and then spawn2. And spawn2 might lead us to understanding how it injects in memory, how it bypasses AMSI, any kind of PE metadata. And so we take all that and we can get this from the malleable profiles. And so if you don't know what a malleable profile is or have seen one before, Cobalt Strike's webpage has a deep dive into that. Some of the more used profiles are from the GitHub page or the repository from Threat Express. And so I always like to ask people questions, what products do you have in your stack that will provide visibility into these three things, or more than just the three as well? And we also have produced attack data from Cobalt Strike. So if you haven't familiarized yourself with the data or how it looks over the wire or how it looks from an EDR tool, we have three different data sets here that you can dig into as well. All right, diving into a little bit more of the malleable profiles themselves. So I went and I collected all of the public profiles on GitHub, which could be mixed of Threat Express and anybody who's ever created one. Even Cobalt Strike has a large portion of their profiles public. And we can dig through these and pull out data like the spawn2 process, the pipe names. We can look at like DNS idles. We can see if any of like the stager, different pieces of the stagers are different or changed based on versions and things like that. So that's the value of looking at the profiles. And this is like probably the more important pieces of the profile to look at, which would be like pipe, spawn2, and the DNS data, the DNS beacon, and the DNS subdomains and whatnot. So the default Cobalt Strike values are public. They're very known. The network stuff is obviously very specific. These are hard-coded and they will be found in the data as they're traversing the network. So if you're looking for DNS type traffic, this is where it would be. The named pipes, there is a common pattern. There's only 6 of them that are default for Cobalt. It will use these dependent upon what is executed by the operator. And then the default spawn2 process is run DLL 32. If you're looking at a Threat Express profile, it's typically DLL host. So based on what I found in the wild, all the profiles on GitHub, things like that, the most common spawn2 processes are on the left. And like I said, you'll see DLL host, GP updates very common, regserve, run DLL 32. Those are all very common. to be found within public profiles. And then again, on the right-hand side, these are all public pipes that are used. RPC, half duplex, all of these. Obviously, the defaults will be mixed in here too. Note the reason why these are used and the reason why you have a malleable profile is to blend in with normal network traffic, endpoint process behavior and lineage, standard default pipe activity. These pipe names that you see are all default pipe names that are used by Windows and other like applications like browsers and whatnot. So these will blend in and they can be very voluminous. So be careful when you're writing content based on these couple things. All right, so within Splunk, we splunked our findings. We found about 253 command and control servers, 23,000 data points we have based on this. There's certain watermarks that are out there in the wild, and watermarks can be based on the license, air quote license. So it just depends. And then over time, we've seen certain license used more. There's an uptick in certain like leaked versions of the software. And then the top C2 host headers is exactly how it sounds based on the profiles that we've extracted using Melting-Cobalt. These are the top C2 domains that are being used out there today. So kind of common. You can see here at the top is that wmsj.cn and then so forth down below. And then I wanted to show sort of like the most common spawn 2 processes that organizations will run up against. So on the left, bottom left, most commonly you will run up against run DLL32, DLL host, and GP update. Those are the highest percentage based on the data that we have. Most common ports, again, it's going to be 443 and 8080 or 8443. And then for DNS idling, which we'll talk about a little bit more in a minute, most common IP is going to be quad 0. And then the most rare spawn 2, ones you probably won't run up against in an organization, is going to be like app launch or SPL WoW 64. Very rarely used. So just something to kind of keep in mind. I wanted to show just percentage wise what you would probably hit. So diving into writing content based on the spawn 2 value that we capture. This in particular, I simulated with Cobalt Strike. So by default, again, it's run DLL32. You can change it by using, say, the Threat Express Malleable Profile, which is the jQuery one. What I did is I executed what's called the bacon, bacon. I ran this binary. I then ran a couple commands in Cobalt Strike, like dump hashes. I then did a jump psexec 64 to a host and using the HTTP listener. And then I ran shell who am I. And so you can see in the screenshot here, I ran bacon from my desktop. It had a couple things that changed here, which is going to be that 3C file spawned run DLL32, and then run DLL32 spawned command.exe. And so that right there, the run DLL spawning command is going to be the default spawn 2 process. So anytime you run jump, is going to be when run DLL32 spawns, and then when you run a command like shell who am I, it will spawn off of run DLL32. So it stands out pretty well. And another thing we'll look at here in a second is that when this happens, a couple things occur. So digging in a little bit further here, the obvious here is that command/C spawned from a non-standard process. So if you have any kind of baselining in your organization, you'll know that command.exe does not typically spawn from a run DLL32 process, or most likely, for that matter, any system32 process. So that's something to keep an eye on. Another thing would be looking at randomly generated process names like that 3C05. We can also track based on that behavior. There is a service start event code 7045. You can look at anything that's hitting over admin $, and obviously any named pipes. The named pipes in this particular case is coming off of run DLL32. And so kind of like looking at baseline wise common processes that spawn run DLL32, processes spawning from system 32 processes like command or PowerShell. And then we should be able to find that netcon to the team server, any other file mods and registry mods all come from this spawn2 process. And so now I'm kind of like shifting and showing a little bit more here. This is the 3C05 service name being started, and its path is on that admin $sign. So that's why it's important to look for this. And this is with event code 7045, the first screenshot. The second screenshot below is event code 12, 13, and 14 from Sysmon, looking at the 3C binary. And so you can see here, it's putting itself into the registry, which current control set services as a new service. And its details is admin $3C. So kind of just different avenues here. You're looking at registry, you're looking at service creates, things like that. All of this stuff stands out as, you know, a randomly generated process name. And this is default behavior of Cobalt Strike. So when that spawn2 process is spawned, it's sacrificial because now it's happening, its behavior and adversary is performing. There's typically never a command line, and by default, the netcon will egress from run DLL32. So we kicked off all this behavior. What does it look like? So a simple analytic that we created literally looks for run DLL32 with no command line values. And so we see that here. Now, it could be a little noisy sometimes. Sometimes run DLL32 spawns without a command line. So we went one step further by using a join. And so this join will cross it to the network traffic data model. So now we're looking for run DLL32 with no command line. And then we're combining it through that join, the network traffic based on the process ID. Sometimes it might be process GUID. So it just depends on what EDR tool you're using. But we'll combine that with there. So now we can get the process, the parent process, which is 3C, the process, run DLL32 with no command line arguments, and the destination port and the command and control server, which would be our team server. Remember, this is all default behavior, so it all stands out pretty well here. Okay, now digging into the pipes, named pipes in general. Again, on our left-hand side, these are our default pipes, post X, status, underscore. These stand out pretty well, and they're very easy to hunt for. Most EDR tools have this built in. Sometimes, depending on the EDR tool, like Sysmon, it has an actual event code just for named pipes. Some EDR products might look at it as a file modification. So it's something to kind of be aware of and how your tool sees it and uses it. And then on the right is our in the wild named pipes. These particular named pipes, again, blend in very well with standard Windows behavior. So I'm showing now just kind of like pipes going wrong. This particular query is just using Sysmon event ID 17 and 18, and then I put in all the default pipes and some additional pipes so that I could show some noise here in a minute. But you can see the 3C process hitting the MSSE named pipe. My bacon one is hitting post X, and my run DLL32 is hitting post X as well. And then the values, if I go back here, typically on the in the wild pipes and with the default pipes, you see those pound signs. Those will mean auto-generated values, randomly generated values. And so that's why over here we see like post X underscore CFF0 6944 7439. So the values are auto-generated and it will be just random every time. So just beware, again, with these in the wild pipe names, Mojo, things like that are all very heavily used by default native Windows processes. And so here is a screenshot of like service host hitting SCE RPC, Explorer hitting the UIA one, things like that. And then over time, this is a wider range of time that I have on my box. I think it's 24 hours. But you can see like WKS service, SRV service, LSAS. Those are all very noisy. PowerShell hits a named pipe. So it can be very voluminous. You got to be very careful in writing content for this. You do not want to blow up your alerts page with just random pipe names. Okay, so now on to DNS beaconing. Now, this comes straight from cobaltstrike.com page where they discuss all the default values. This is important because you'll see all of the kind of like the default subdomain of like CDN dot, or if you're using IPv6, www6, or TXT records uses API, things like that. All of these are important to understand because this is what will help drive analytics or detection into these types of things. Note, Cobalt Strike can use A record, TXT, quad A. I believe that's it. But yeah, so once you get that, once kind of you see all this data here, we can switch into kind of how DNS beaconing works, or what to look for as far as patterns. So the default patterns, again, it will use a quad 0. An endpoint will beacon, which is called the DNS idle. It will beacon out the quad 0 until it receives a response. So some EDRs may pick this up. Quad 0 looks a little fishy. But then once you actually start to see a beacon going out to quad 0, it looks highly suspect. And then from there, you'll see a request like CDN or API for TXT records. I found that TXT records are extremely noisy and when it's beaconing back and forth or collecting data. And so then on the right-hand side of our screen here is the jQuery profile from Threat Express. These are the settings that they change things to. So again, it's going to look a lot different than the defaults because they're trying to blend in. But you can easily see quickly that based on this, you might be able to write a signature based on that pattern. So again, back to the DNS idle. On the right is a screenshot. Most profiles by default hit a quad 0. There are some that will hit quad 8s or 8844. Some of them have like a straight Google IP, and then there's just some random other ones out there. But typically it's quad 0 you will come up against. So if you were to say, hey, like who's beaconing out or what endpoint is hitting a quad 0 IP, it might be highly suspect at that point. What's going on? So it stands out. And so then I mentioned like API and CDN. These three on the bullets right here are like actual events from my environment. And you can see it's just randomly generated in between each dot. So CDN dot random numbers, post dot long random number, things like that. So they kind of go on and on. There's just a lot of noise. What I found with like a TXT endpoint is TXT records will be extremely noisy, and I'll show you that here in a second. Just another quick screenshot of what the post looks like and how the domains and everything like that are very long. And then TXT records, if you're using like Zeek or anything that collects the DNS request data, this stuff, and you can actually see the TXT record being requested, you'll see that it's just a bunch of what looks like base 64 data going across, and it's all scrambled in between each request. So every single one of them will have to be put together. And you can see on the left under time, you will see that it beacons out, I'd say almost less than 0.1 second, right? So it's very, very noisy. If you have a analytic that looks for high volume of TXT records in a minute, one endpoint will easily stand out, no problem. And then you can see based on the record, the name of the domain and whatnot being requested will obviously stand out at that point of being something suspect. So tips for hunting, again, just mentioned about noisy TXT requests. Why? What process is it? Why is the data weird? Base 64? Is it encrypted? Is it mumbled? Maybe I don't know what it means. So TXT stuff is very suspicious. A records, hunting the defaults are easy. Unfortunately, a lot of the profiles do change, how these records and requests look. Simple hunt queries, if you're using like Suricata or Zeek, just look for API, CDN, or post. And you can even stack those, right, by, who's making so many of them. So like the second query here is just looking for 500, greater than 500. So it'll stand out really fast, especially for TXT. But anybody hitting the defaults obviously will look very suspect, and you can look at the domain, research the IP or domain and see if it's been found or prior seen related to Cobalt Strike. So some of the key takeaways here. Splunk Melting-Cobalt can absolutely help you stay ahead of the curve of actor tradecraft using Cobalt Strike. So we can take those malleable profiles and convert it into security content, which is great intelligence. And you can also enrich it using something like Shodan or any other tool, add more data to it. You can Splunk this data, which is what we did. We actually have a dashboard you can grab here along with an inputs conf. So if you're running your own scanning, you can pop these right into Splunk and start Splunking this data right now. Thank you so much for listening.